Now let's summarize the behavior of elements in all groups or most groups of the periodic table. We are summarizing chapter 8 with this. So the first group is group 1, otherwise called group 1A. This one will include the hydrogen, lithium, sodium, potassium, cesium, those ones. These guys in blue, and rubidium. They tend to react by losing one electron. So if you're starting with a metal M, he loses one electron to give you a metal cation M+. An example can be given of lithium. Lithium loses one electron to give you lithium plus the one electron lost. And that applies to the rest. If you want to talk about potassium, it will do the same. K gives you K plus one electron lost. Okay. Now, we are going to focus on those that have Sec2 energy shells and above, which means we don't want to consider hydrogen in this case, which only stays at 1s1. So if you're looking at a metal starting from lithium, with the exception of hydrogen, because that one is in period 1, we want those that are period 2 and above, which is what we mean by n is greater than or equal to 2. Those metals tend to react with water vigorously to give you hydrogen gas. Okay. And by the way, there's a lot of heat generated, which generally leads to formation of a fire, creation of fire. Okay. Now, if you take a metal from the main group 1 element, for example, if you take, let's say, sodium, and react it with oxygen gas, you expect to get sodium oxide or metal oxide having this formula. But because you have to balance things, we'll have to put 2 here, and oxygen is not happy, so 2 is not working for sodium here. So we'll have to put 2 here to balance the oxygen, and doing so, we now have 4 sodiums, so I put 4 here, which is why you see 4 here as a leading coefficient. There's 1 implied 1 balancing the oxygen, and there's 2 balancing the metal oxide. So that's the general characteristic of group 1 elements. Now for this first equation, I need to give you an example of reaction of a group 1 element with water. So if you take the same sodium and react it with water, solid sodium that is, it's supposed to give you sodium hydroxide and hydrogen gas. I have one hydrogen here. I have 2 hydrogens on the left. I have 2 hydrogens on the right. Not 2. I have 3. There's 1 here and 2 there. So I have to put 2 here, and I have to put 2 here and here to balance everything out. Now, if you check, you have 2 oxygens, you have 4 hydrogens, and everything is good. So you get sodium hydroxide, which is soluble. So we say aqueous. Okay, this is how they look. This is how lithium looks. That's how sodium looks. You can carry it with a knife. It's brittle. And potassium, you know why they are hiding it in a capsule. It's very reactive. The rubidium is right there. That's our rubidium. And this is our cesium, how it looks. Okay. Next, in line, we have the alkali earth metals. We'll talk about their properties. So M stands for the metal, and M2+, that's the metal cation. You can tell why it has a 2+. It's because they lose 2 electrons. They belong to group 2A. They have a valency of 2. An example is given here. Let me use magnesium. We talked about this. When magnesium loses 2 electrons, you get Mg2+, that's balanced by 2 electrons. That is an example of that. Now beryllium and water, usually there's no reaction, but magnesium and water will give you magnesium hydroxide and hydrogen gas lost. Okay, so generally if you have a metal from magnesium going down, not beryllium, so magnesium going down should react with water to give you magnesium hydroxide. and hydrogen gas. So here you have the metals that will do it, including Mg, including magnesium. And these are the looks of these alkali earth metals. Starting from beryllium, it looks like that. Magnesium looks like that. You must have seen magnesium ribbon. Calcium, it's whitish. Mostly that's the element that gives the bone strength. Magnesium is found mostly in plants inside the chlorophyll. You have strontium, you have barium, okay, and then you have radium that looks so nice. Look at radium, looks so nice. Okay, so now let's talk about main group 3A, aka overall group 13. It includes boron, aluminum, gallium, indium, and I think TL, that should be thallium. So again, we'll focus on these elements that are starting from the second period going down. Their energy shells will be greater or equal to 2. So we have to have at least n equals to 2, and we can go further. 2, 3, 4, 5, 6 is going to n equals to 6. Okay, so we are talking about this block of elements, and an example is going to be given of aluminum. So aluminum is going to be a representative element in a reaction with oxygen. We call this reaction oxidation. Why? We are adding an oxygen. When Al reacts with molecular elemental oxygen, it gives you aluminum oxide. That's the formula of aluminum oxide. We say that aluminum has a charge or oxidation number of +3. Oxide is always 2- because the oxygen is somewhere here. It's 2 steps to neon, so he gains 2 electrons, so it's 2-. Drop the 2, drop the 3, it's gonna be Al2O3. Now all that will be left is to balance. You realize that you have to put a 4 here, a 3, and a 2. That will be aluminum oxide product. Aluminum metal reacts with an acid, for example sulfuric acid or HCl. This H plus is an acid, is representative of an acid. So when Al reacts with H plus, he gets oxidized from oxidation state 0 to oxidation state 3 plus. This process right here is oxidation. The acid itself is going to be reduced. The acid H plus is going to be reduced to H0. So from H plus to hydrogen gas, that is reduction. So this reaction right here is a representation of a redox reaction where reduction and oxidation happens at the same time. Those are 2 representative reactions we can show based on aluminum in overall group 13 or main group 3A. Now you're looking at examples of samples of boron, aluminum block, gallium. Usually gallium melts when you hold it in the hand, and then you have indium. Those are 4 examples from main group 3A or overall group 13. Now let's talk about group 14 or main group 4A, because we count 1A, 2A, keep this, 3A. Now we are on 4A. It includes carbon, silicon, germanium, tin, and lead. Okay, so this is tin right here, or stannene. SN came from the word stannene, I think it's Greek, so they chose the S and N as a symbol of it from Greek. Reacts with an acid to give you SN2 plus. Any element in the periodic table before it reacts has oxidation number of 0. He has increased to 2 plus, so this process is oxidation. Oxidation is increase in oxidation number. The acid H plus, or rather proton, goes from +1 to elemental molecule hydrogen gas with oxidation number 0. That is reduction. So again, you're looking at an example of a redox reaction here. Lead, or Pb, starts with oxidation number 0, reacts with an acid to give you 2 plus. Okay, so the number increased. This is oxidation. The acid with H plus decreased to oxidation number 0. That is reduction. Okay, another example of redox reaction where reduction and oxidation is happening at the same time. Okay, carbon looks like this. You've seen charcoal or coal before. This is diamond. I don't know if you've ever seen diamond. I've seen enough of it. And then this is silicon, what they use in Silicon Valley to make electronics. You have germanium, you have tin, and then you have lead that is used in so many things, including batteries. Then we are on main group 5A, where you have nitrogen, phosphorus, AS, SB, and bismuth. So if you look at dinitrogen pentoxide, a solid form of dinitrogen pentoxide, if it's put in water, it dissolves to give you what we call nitric acid. That's one property of the compound of nitrogen. And then tetraphosphorus decaoxide, tetraphosphorus because it's 4, decaoxide because you have 10 oxygens. The solid form of it in water is gonna give you phosphoric acid. Nasty stuff. So it's an example on how these have reacted, the nitrogen and phosphorus. And then this is how liquid nitrogen looks like. It's usually very cold, freezing cold. You have white and red phosphorus. One of it is cheaper than the other one. You go research, you would know. Then you have arsenic, you have antimony, a rare one, and then you have bismuth. That's how these elements look like. Now we are on the group with oxygen, sulfur, selenium, tellurium, and polonium. This is main group 6A. An example of a molecule, sulfur trioxide, put it in water, is gonna give you an acid called sulfuric acid, a very strong acid. That's an example on how sulfur compound reacts. Oh, by the way, we've done so many examples with oxygen. Oxygen is found in water, and oxygen oxidizes aluminum to aluminum oxide. Sulfur looks like this. It's usually elemental as S8. You saw this in the practice exam 1A. And then selenium looks like that, and then tellurium looks like that on a watch glass. Next, you're looking at group 17, main group 7A. You realize that it's main group 7A because the valence electrons is 7. X is always used by chemists to refer to halogens. Group 7A elements are called halogens, maybe because they make salts. So when you add hydrogen gas to a halogen, you're going to get a hydrogen halide HX. The example I'm going to give you is hydrogen gas reacting with chlorine gas to give you 2 molecules of hydrogen chloride, hydrogen halide, hydrogen chloride gas. And this one, if it's dissolved in water, it gives you hydrochloric acid aqueous. Similarly, hydrogen gas and bromine gas, bromine liquid bromine, or fumes of bromine gas is gonna give you hydrogen bromide gas. If it's dissolved in water, it's gonna give you hydrobromic acid. Okay, and this is how they look like. Nasty gases. I think that one's supposed to be chlorine, as I see. This is supposed to be bromine, as I see, and this is iodine that sublimes. We talked about this in chapter 102. It changes from solid state to gaseous state without forming a liquid. That's what we call sublimation. And then lastly, we have main group 8A. If you add 2 plus 6, you're going to get 8. Those are noble gases. They do not gain electrons. They have very high ionization energy of all the elements. They have no tendency to accept electrons. They have no tendency to lose electrons. So high ionization energy for sure. They have completely filled orbitals and subshells. They are inert. They are inert. They do not react. They are called noble gases, but they are also called inert elements because they don't gain, they don't lose electrons, they don't ionize. Okay, compounds of noble gases. You have xenon tetrafluoride, xenon trioxide, xenon tetraoxide, xenon with an oxygen and F4. I forgot the name of that. They exist. A few krypton compounds like krypton difluoride, for example, has been prepared in the lab. Let us now compare group 1 and group 11 elements. Now, I'll use the example of sodium. Sodium has 11 protons, meaning it's going to have 11 electrons with electronic configuration 1s2, 2s2, 2p6, 3s1. Focus on the s1. Now, if I take copper, which is Cu, this one has atomic number 29. So I'm going to use the shortcut of argon to take care of 18. And then it's going to go to 3d10 for S1. That is for copper. Again, you see, you have an S1. If you look at silver, Ag, with atomic number 47, meaning he has 47 electrons, the noble gas electronic configuration will be that one of krypton. Krypton is here, argon is there, so I use the krypton as a shortcut for silver. Krypton will account for 36 electrons. Then out there, I'm going to have 4d10 and then 5s1. Again, all of these have a common outer orbital called s1. All right, so you remember again, the valency of group 1 elements is 1. Okay, most likely it's going to be S1, outermost orbital or subshell. And so you're seeing these ones will also have S1. So the metals in these two groups have similar outer electronic configuration with one electron in the outermost s orbital. The chemical properties are quite different due to difference in ionization energies, correct? These ones will readily react to lose the one electron compared to the copper, silver, and such. So ionization energy, we said increases across the periodic table from left to right generally. So we expect group 1 elements to have less ionization energy. They easily lose the electron compared to group 11. So let's look at properties of oxides across a period. We just determined that sodium will form an oxide called Na2O, and we've determined that aluminum will form an oxide called Al2O3, aluminum oxide and sodium oxide. But you can have all other oxide depending on the valency of the metals and how they will exchange the charges to give you these chemical formulae. So anytime you have a metal and a non-metal, you expect that the bond between the metal and the non-metal to be ionic, the metal being something like sodium, the non-metal being the oxygen. So those are metals. Okay, these are metals, so their metal oxides will be ionic, but the other ones tend to be non-metals like silver, silicon oxide, tetraphosphorus, deca oxide, sulfur trioxide, dichlorine heptoxide. Okay, so you have a non-metal and non-metal. You expect to have molecular structures. In terms of structure, the ionic compounds are usually extensive in 3 dimensions, but for molecular ones, they're going to be discrete. In fact, you're going to see SO3 as a gas. And then the melting point of ionic compounds tends to be higher than the melting point of molecular structures because ionic bonds are stronger than intramolecular forces. You're comparing intramolecular forces versus intermolecular forces. They have to be stronger. Intramolecular forces are usually stronger And then the same applies for boiling point. It's going to be higher for ionic compounds. And acid-base nature, usually sodium oxide, you drop it in water, is going to give you a base, and then aluminum oxide is amphoteric, depends on the environment. It can be acidic or basic. Usually for these molecular structures, they tend to be acidic because they can give you silicon hydroxide, which is acidic, for silicon oxide in water, phosphorus, tetraphosphorus decaoxide can give you phosphoric acid, SO3 can give you sulfurous acid, dichlorine heptoxide can give you HCl or the derivatives of HCl, so it will be acidic. Chemistry in action, discovery of noble gases. You've seen people using glow sticks. So helium looks like this, neon looks like that, argon like that, krypton and xenon, they look almost similar, but the krypton seems to be quite brighter. You did an experiment on spectroscopy. If you've not done it, you'll do it, but this class has already done it, and you checked for the electromagnetic spectrum, the emission lines for, I think, these three you did. And you used colored pencil to draw the emission lines. You see how bright they are. And you are asked to describe the color that is emitted from the emission tube. All right, so spectroscopy helped in the discovery of these noble gases, and you're looking at Sir William Ramsay, who played a big role in this. Classify the following oxide as acidic, basic, or amphoteric. Okay, so if it's a group 1, I expect it to be basic. Okay. The reason is this. If I split up Rb and oxygen, I give the RbOH minus, is gonna give me rubidium oxide. I give the oxygen H plus, most likely is gonna give me water. Water is neutral. This right here is a strong base, so I expect this to be basic. Water is neutral. Hydroxides of group 1 elements are strong bases, so this will be basic. What about beryllium oxide? Beryllium oxide contains beryllium, which tends to be the first element and might have some boundary characteristics. This one can play the role of both acid and basic oxide. Just to be memorized, memorize it similar to aluminum. We say that aluminum is amphoteric. Amphoteric because it can behave both ways. Remember, when you talk about animals that can live in water and land, you call them amphibians. So this is amphoteric because it can behave as both. As is a p block element, and if it's a p block element, most likely is a nonmetal. Nonmetal oxide tend to be acidic. Okay, so you can read the text and explanation, and that's it.